Hello, physics students. Sorry I couldn't be there today, but we're going to spend just a few minutes talking about electric fields. Electric fields aren't like a physical field like you might picture where someplace you could go find grass or something like that. An electric field is a concept that scientists have created that will help them be able to explain the movement or the forces that a charged particle would feel when placed near other charged particles. So an electric field is used to describe specifically the direction a positive charge would move when placed near some other charged particles. An electron, which is a negatively charged particle, will always move against an electric field. A proton, or a positively charged particle, will always move with the electric field. The main rule behind an electric field is that it's going to point out of a positive charge and into a negative charge. The electric field lines will start at the positive charge and they will radiate out. They will point out away, as you can see on the left. On the right, you can see that for an electron or any negative charge, they're going to point towards it. The field lines will end at the electron and they will start at the proton. Out of positive, into negative. All charges, positive or negative, will create an electric field, and a charge creates an electric field that extends out throughout space. It's always strongest the closest you are to a charge, and it's also always symmetrical. Electric fields have a direction. There's those arrows, out of positive into negative. That means they're a vector. And we will, in your virtual lab later today, do examples of multiple charges that can create a net electric field when they work together. When you're drawing electric field lines, I kind of talked about this, but here's it written down for you. The lines begin on positive charges or they begin super far away for a negative charge. And the number of lines that are drawn help you see how strong the field is. And the last rule for electric fields is that field lines from the same field will never cross. They'll never intersect. Here's an example of an electric field that would be created by a positive charge and a negative charge. The electric field lines are pointing out of that positive charge and into the negative charge. And if we put a proton, a positive charge, right between a positive and negative, it's going to want to move as far away from the positive charge as possible and as close to the negative charge as possible. If you start approaching it at some angle, the charge will kind of want to move away from the positive charge, but then it will get pulled back into the negative charge, which is the reason that the electric field takes that shape when it looks. But it's going to come out of positive into negative. Here's an electric field created by two positive charges. It's pointing out of both positive charges. Sorry, I'm recording this during lunchtime. We could think about, what if we put a positive charge or a proton right between those other two positive charges? There's going to be a moment where there's no electric field. We can see that because there's no lines there. But the positive charge would feel a force of repulsion that's equal to both charges. It wants to move to the right and the left. And as a result, there's going to be a net electric field of 0. We're going to do some examples of this on the next couple slides, but we're going to try to connect electric field to Coulomb's law. A big idea to keep in mind for today is that electric field is newtons per coulomb. Remember, Newton is the unit for force, and Coulomb is the unit for charge. So an electric field is a force divided by a charge. Last time we talked about Coulomb's law. F equals K, that was a constant, Q1, Q2 over R squared. Q means charge. That was the weirdest thing, and R is the distance separating them. But we can think about an electric field helps us figure out what direction the force will go, which way will the charge move. And then we're going to place a test charge to figure out which way it will move. There's the two equations. I actually will give you both of these on your test, although it's just the same equation rewritten. An electric field is a force divided by charge, and a force is a charge times an electric field. Here is our first example for today. What is the force of a positive 6.5, I'm going to circle that prefix, microcoulomb charge, would experience in a uniform electric field of 25 newtons per coulomb? We talked about 3 prefixes last time, milli, micro, and nano. You do not have to have these memorized, but you do have to be able to use these. Milli means 10 to the negative third, micro means 10 to the negative 6, nano means 10 to the negative 9. So I have a charge of 6.5 times 10 to the negative 6 coulombs, and it's in an electric field of 25 newtons per coulomb. If I want to find the force, I would think force equals charge times electric field. The force is going to be 6.5 times 10 to the negative 6 times 25. And then I'm just going to type it in my calculator really fast. 6.5 times 10 to the negative 6 times 25. I'm getting a force of, I'm going to write this in scientific notation, 1.625 times 10 to the negative 4. Force has units of newtons. We can also find the electric field created by a point charge by using the formula E equals K. That's our constant, 9 times 10 to the 9. Q, that's the charge that's creating an electric field, divided by R, how far away you are from that electric field. And R is going to get squared. This is very similar to the equation we did last class, KQQ over R squared. For finding a force, we need a charge that's creating a field and a charge that's experiencing a field. For an electric field, we just have something creating it. You could have an electric field and theoretically not have a force if there's not a second charge there to interact. So our last example, we're going to find an electric field that's at a distance of 1.25 meters. Here's my R. From 6.5 microcoulombs. 6.5 times 10 to the negative 6 is my charge. So to find the electric field, I can use that. I'm going to zoom in here. E equals K, Q over R squared. The electric field is a constant, 9 times 10 to the 9. The charge was 6.5 times 10 to the negative 6. And then I'm going to divide by the distance that I am away, 1.25, and square it. Okay. Now I'm just going to multiply in my calculator. This is one I would definitely try calculating sooner than later because there's some little things to be careful that you're entering it appropriately in your calculator. But you'll get a pretty big electric field. That's okay though. 37,440 newtons per coulomb. Now that we found that electric field, the next question says, what's the force? A positive 7.5 microcoulomb, here's my new charge, would experience at this position. Well, I can use the formula from the last slide. F equals QE. Sorry, I guess it was a couple slides ago. The force, I'm going to put a 7.5 micro. Micro is 10 to the negative 6. Hello. And then multiply by my electric field, 37,440. And I'm just going to multiply. And I'm getting 0.2808 newtons. There was your quick introduction to electric fields. This should set you up to be able to do the virtual lab.